Google has been going bananas, and I mean literally. First it was nano banana, and then later on it was paper banana, and now they have vision banana. Let's go find out what vision banana is all about. So welcome to the series on decoding papers with AI, where we take papers, feed them to AI tools, and try to decode or understand what the paper is all about just using AI. So let's jump right in and find out what Vision Banana is all about. So I first came across Vision Banana on X from a scientist in DeepMind. It says, introducing Vision Banana, an image generator that achieves state-of-the-art on segmentation, depth prediction, and surface normal estimation. So they're also given a project page and also a technical report, which of course we'll be going through. And so here it's an illustration. Generate a segmentation and / depth surface normal visualization of this image using the following color map, right? So you can see that this is the image. So this would be the semantic segmentation, which would segment each object, a background parts, and everything into like different segments. So you can see how the person is colored red, and then the sky is colored like blue, and so on. Instant segmentation is like a very closely related. If there are multiple instances of people, they would all be like colored differently. So you can see that in the previous one, this one had same color for all three people in persons in the image, whereas here this is like for instance of one instance of the person, the second instance of a person, and the third instance of the chest. It's basically showing that there are three people here. And of course you can also have a different object and you get different maps. And this is reference expression segmentation. So maybe this is the expression of like the person jumping or something like that, skateboard. And the depth estimation shows like the person, like how far close the person is from the, from in the image using the depth map. And surface normal, this is slightly different, like more. I myself like forgot like where you have these normals from vectors from different parts of the image that shows up. So you could see that for this, it's also like closely somewhat similar, has some similarities with semantic segmentation, but it's mostly like vectors and surface normals coming out of surfaces in the image, right? So you can see how these surfaces all like show up very nicely here and in these kind of things. So that's the first thing. And then it says that recent image and video generators seem to display zero-shot capabilities on computer vision tasks such as segmentation or surface normal estimation. But how can we quantitatively evaluate these capabilities? Can we get an image generator to reach state-of-the-art on these tasks? So then it says that we reframe the classical perception tasks such as image generation and instruction turned the Nano Banana Pro. And then what they got was a generalist model that beats domain specialists with specific architecture and not custom losses. So this is a photo, and then you can see how the Vision Banana had estimated depth for this photo. What generative pre-training did to natural language processing applies also to vision. So you've seen how the vision transformers came via the same statement that he's mentioning. So training on editing examples such as removing the chair from this image implicitly teaches pixel perfect segmentation. Similarly, generating realistic shadows requires deep 3D understanding. Image generation is becoming the universal interface for computer vision, just as text generation did for language and reasoning. Generative vision pre-training is paving the way for foundational vision models. So that's it. So that's the Twitter or X thread for this. So next, what we'll go and check out is this project page and then the technical report. So we're at the Vision Banana project page. So it says image generators are generalist vision learners. And this is from Google DeepMind. So it says Vision Banana is a state-of-the-art unified model for both image understanding and generation. Generative vision pre-training is an effective paradigm for visual understanding, and image generation serves as a universal interface for diverse vision tasks. So from what I understand, this is like a unified model which can do both understand images as well as generate images either based on the understanding or even based on the prompts. It's like unified one model which can do both, right? Because previously, if you think about it, you have some really good vision language models which can really understand things very well. And what you had is we also had image generation models starting way back from like DALL-E to like Stable Diffusion, and then you had a lot more other ones like Midjourney, and then like more recently we have Nano Banana from Google, as well as ChatGPT's image gen. So they just released an image gen version 2 like just a couple of days back, which has been really impressive. But this actually reminds me of another model, right? If it says that Vision Banana is state of the art for both unified vision and things. So this reminded me that way over a year back, right, there was DeepSeek, which came out with DeepSeek with Janus, if I remember correctly. So Janus was also like a unified model which could do both image understanding as well as image generation. And this was quite some time back, and I have not seen much updates on from Janus since then. But this was, at least I remember that this was quite some time back. DeepSeek had this Janus, which says unified multimodal understanding and generation models. So it's interesting that like Google has come out with Vision Banana like long after that. So this is the Janus model I was talking about. It says Janus series unified multimodal understanding and generation models. So this is almost 2 years back, not even a year, and this has like 17,000 stars, so an MIT license and so on. Interestingly, DeepSeek just had the V4 released this week, which has also been really like all over the news as well, right? So Vision Banana, from what I'm seeing at least from the overview, is this one unified framework which can do both image understanding as well as image generation. So here you can see the generation part, and here you can see the understanding part. So that's like what we have here. So let's take a look at some of the capabilities that it says, right? The first one is semantic segmentation. So semantic segmentation is basically you segment the image into like different segments. So it says generate a visualization image of semantic segmentation using the color mapping cat ears less than 255. It's like very specific, and then 255, 165, and then greater than 0, then exit sign. So they provided like a 0, 0, 255, and then background is like anything between like 125, 0 and greater, something like that. So they're giving very, very specific like range values here. And you can see that when you hover over them, you can see that the cat ears are you can see this is like the cat ears, and then perhaps there's also the exit sign somewhere. So yeah, see, exit sign is now in blue, so this is the color they have given for exit sign. And then and the background is it's given basically this color. So yeah, it's not the range but rather the color. So there are just three. So this very clearly says that generate the image into 3 segments, and these are the colors that they want. And it's very accurate, right? So it's also amazing. Of course, this is an example, so they would want to keep it accurate. Here's another prompt illustration of the same thing. So so here it says, instead of, if you don't want to give values, you can also give this in text, right? It says cat red, lock is going to be pink, exit sign is going to be light purple, and background is going to be yellow. So let's see what this one says. Okay, you can see here, right? Cat is now all the cats are red. Exit sign is like, light purple, background is yellow. And what was the other thing? Like the lock was pink, right? So this is also like very, very specifically, you can just everything within. So what I'm seeing is that I remember like a couple of years back, I still review papers from like CVPR, ICCV, CCV, and so on. There was this transition of VLMs from object detection, semantic segmentations, to making them all like VLM, like basically prompt. You can just prompt and make it all unified. But then lots of papers were trying to address that. But then after some time, there was a little not too much advances there. So now I see that it's back again. So, and then Vision Banana is probably one of the first things to do that. So here's another example. So this is going to be a little, like lots of details here. The image is a pre-class labeling. So it says macaron cakes are represented. Again, this is by color. So let's go to the like there you can also specify color using these I think HTML codes or something, if I remember. So it says these are the colors here, the slice cakes are this color, and so on. Why this is easy and important? Because if you're doing like web programming and web, like this is so easy to just put it right there. You can easily like call some API and then ask these parameters could be passed in, and you would get what you would want to display. So it's very nicely, you can see this is the macaron cakes are 25250, which is yellow, and the other ones also have come out really well. And let me just try the prompt 2. Prompt 2 is like, instead of that is red now. So right, so this is the like I forgot the exact name. In HTML you used to use these codes, so you can see that everything is now red. The whole menu itself, that's amazing. All the food items have now become red, right? So that's pretty cool. So anyways, and the dessert, what is the dessert? Dessert is this color. And what's the dessert here? So whatever is the dessert, so that's okay. I think this is the menu, right? And this, all of these are the 800 is red. Those are all the food items. The menu is green, and anything else, the patterns on the wall is like these colors. So it's pretty amazing. So then there is instant segmentations, right? So instant segmentation basically does, you can also tell how many, counting of this, generate an instant segmentation of this. Each price tag is colored differently, so you can see that these are the price tags here. So all the price tags are now colored differently. And what does prompt 2 says? This is an image segmentation task derived from the input. The crescent-shaped croissant instances are each represented by unique solid color. Background is RGB. This is the color. So they're giving a color for the background, and they want all these croissants to be different colored based on the instances. So there are how many, like 12 croissants in the middle. So let's see how many we get. So you can see all the croissants are in different color. This is very close, but they are different colors as well. So very, very nice and very like intuitive, right? This is pretty cool. So I'll skip the next image because it's going to be like bottles and so on. So I mean, or maybe just quickly do it. This is one prompt, and this is the other. So it's also like pretty cool. So what is the next one? This is reference expression segmentation. So I think this is what I think we saw previously. I'm guessing that this is some kind of an expression, and then how to segment that. So it says input is a segmentation map image. The area that corresponds to the man in pink t-shirt is rendered solid white. The other man is rendered in green. So it's asking the pink t-shirt person to be colored in white, and the other man in green. So you have right there. I wonder why it's called reference expression, but I think like sometimes these terms, some papers start using it, and then those terms just keep like people start using it again. This is another segmentation map image. The prompt is generate a segmentation map image. The stretching cat is rendered green, and the cat that is cleaning itself is cyan. So maybe it's like some kind of an adjective that goes along with the object subject, like, so that's what it tries to do. So right, so we should get green for the stretching cat, and then for the cleaning cat in the cyan blue kind of thing. So that's exactly what it is. And the next one is, so this one is going to be, these are the ones which are challenging usually, like depth estimation and other things. So let's maybe look at a couple of examples here. Generate a metric depth map of the input image. So basically, like it wants each and every part of the image of every pixel to be like based on the depth map. So we should get some kind of changing 3D depth or something like that. So yeah, this is exactly what we're getting. So you can see how it starts off with green and slowly shades away, and then it goes further blue. And it's amazing that this wall, which is supposed to be like kind of almost, it is still at an angle. So there are parts of the wall which are the same and parts of the wall which are not. So all of those are like neatly like captured here, right? So that is the other one. So let's see this, another image will also be good to see this. Predict the metric depth map of the scene. So this is so common in all our like social media photos, right? Visualized in the rainbow, black, red, yellow, greens. Okay, so they're asking us to also giving a color map on how you would want to have the metric depth right away, color palette based. So you can see how the closest one is red. So the person here is on red, then the orange, and then these two are very close. So it's like slight shade of orange. And as you go further back, the last one is white, right? So it's given very clearly black, red, yellow. So there's no black, so I'm guessing that it doesn't have anything like really close, but it starts off with red, yellow, green, and then so on. So that's another nice one. So let's also do another one. So generate a metric depth map of the provided image, right? So this is also like this just takes the default one. Red is closer, dark red is closest, and then like shades of that, and then green, right? So that's another nice image. So surface normal estimation. So this is let's see what this does. Generate a surface normal map of the input image. So when it does that, it shows you, like, say, for these are usually like vectors that are like from coming over from point, and then they are visualized, right? So if you take the car on the right, you can see that these vectors from this surface, they're all having the same surface normal, and then this part is also going to have the same surface normal, whereas this part is going to, so it's basically how the surface, if we take apart, I think from what I remember from my old, it's like if in an image, if you take a surface, which is going to be like a plane, and if you draw normal vectors from it, perpendicular vectors from it, for every surface, how those act are what is called the surface normal. So then another interesting image here, generate a surface normal for the tortoise here. So that's also here. You can see that how almost all this surface is the same, this head is the same, but then you have some variations here because it's changing, right? The vectors would change, the directions would change here. And same way you have like lots of patterns here, the surface normals would change based on these how these sands are arranged. So I'll just click on another example. So this is also like a nice one. This constant here, there's change here, anything flat again is constant, and so on. So yeah, so here now we go to the results. So what we saw so far are like qualitative results. These are like quantitative results. It says it achieves state of the art in 2D understanding. So cityscapes is one of the best methods out there. So this is zero shot though, so that is the most important thing. So there's no, it just does it as it is. There's no like training, testing, all of those. So there are better methods out there which are non-zero shot, so those are not shown here. So then you have instant segmentation. It's a few other data sets are here. So 3D understanding also, it has really good results. So it's what it says. So it's another one, nice. So here this is like surface normal error, whereas this is the average, like the depth, looks like the accuracy, and so on. So that's what mostly we have from the page here. So let's maybe pass this paper through some AI tools, and then kind of see how things move on from here on, like, right? So let's do that. So the first AI tool we are going to use to decode this paper is SaralAI, and it's accessible at saral.democratizedresearch.in. And the first step you do is click on this Saralify, which will ask you to do a simple login. Next, I click on skip for now. If you want to choose which keys, you can use either your system keys or your own keys. And here we can upload our own PDF files. So what I'm going to do is I'll take the Vision Banana PDF file, and I'm going to click on upload. And you can see this is a massive file in terms of file size. It is 36 megabytes. And there are a few options here. So I can either do one-click video, one-click podcast, one-click poster. So let's check out a few of these formats right away, okay? So I'm going to check one-click podcast first. So this is going to generate a very quick podcast on this Fire paper. It's going to take a while, so maybe a couple of minutes or even more. So until that time, what we'll do is let me just go to the paper. This is the paper. Image generators are generalist vision learners. So even the title is pretty cool, and I think this is definitely gonna, they don't call it Vision Banana in the title, but that's what page and project name, everything here. Even here in the abstract, it's pretty much they call it Vision Banana. There are lots of names in this paper. So one name that rings a bell to me is this person, Kaiming He. So he has been like some of the greatest
methods, innovations in deep learning has been from Kai-Ming He, Professor Kai-Ming He, who's right now a professor at, it says MIT, but before that I think he was working at Microsoft Research, and then he had come up, he had been part of works which had some groundbreaking revolutions. Like I think this one is the first one, and look at the citations, it has like some 800,000 citations, right? And then the first one is the ResNet, the famous ResNet. Then there is also residual neural networks, that is how you can make these skip connections, and it has of 320,000 citations. I've used it many times, and it's been a significant when it came out, it was really amazing. And then you have faster RCNN and faster RCNN and mask RCNN. So these are methods for like segmentation, very popular at that time, especially these region proposal networks. When things were coming back then, like how do you segment really images in a very nice way? So these were some of the state-of-the-art methods at that time. Right now we have methods like a segment editing model, SAM, then object detection, you have YOLO, and so on, RFDetect and so on. But at that time, these were some of the top methods back then, and probably also the building blocks for some of the future methods. So yeah, it's great to see that Professor Kai-Ming He is part of this Vision Banana paper also. So here are some of his other papers. Look at these citations, they're like huge. Like at least the first two, faster RCNN and ResNet, these two are the ones which have like ResNet is the first author. So I remember seeing other papers also from him, and this is also a very popular paper, Masked Autoencoders or Scalable Vision Learners. He's the first author, and this is also like I think one of the papers which is Vision Transformers, VIT, right? I think this paper is one which is usually like one of the papers which is highly cited. Basically, this is if I remember correctly, Vision Transformers had really amazing results in text, in natural language process. But how do you change it to if you wanted to do the same thing in images? There are a few papers which got really popular. One of that is this. Another one was an image is worth 16 by 16 blocks or something like that, words or something like that. Anyways, let's get back and see if so I generated a poster instead of a podcast. So this is the poster we got from Saral. Image generators or generalist vision learners, all the authors here, and it's divided this into the whole paper, which was 36 megabytes, has been compressed to the single page poster so that we can get a quick overview of what's going on. So it goes with, while image generators demonstrate impressive visual creation, it remains unclear if they possess strong general purpose capabilities. This research introduces Vision Banana, a generalist model, by instruction tuning the Nano Banana Pro image generator on a mixture of generative and vision task data. By parameterizing vision tasks as RGB images, so this is a nice thing I'm seeing. So the whole vision tasks, the different vision tasks are now being represented as RGB images. The model achieves state-of-the-art performance on a wide range of 2D and 3D benchmarks while retaining its original quality. So it goes on to say that the recent image generators demonstrate emergent zero-shot visual understanding capabilities similar to reasoning patterns observed in large language models. This has been true. I myself have seen lots of vision language models are getting better and better. While generalist vision models have shown potential, their performance on understanding tasks has historically trailed behind non-generative specialized model. This paper investigates whether generative pretraining can serve as a foundation for generalist vision learner through lightweight instruction tuning. So the researchers instruction tuned the Nano Banana Pro base model using a low ratio mixture of original image generation data and additional vision task data. Computer vision tasks like segmentation and depth estimation are reframed as RGB image generation. Okay, now this is really nice. Maybe I read the whole project page. Maybe I missed this point, or this didn't show up there. Computer vision tasks like segmentation and depth estimation were reframed as an RGB image generation problem, right? So you've seen like how image generation is using like aggressive modeling has been like really, or even diffusion models has been like really shown great promise. I mentioned there's so many great image generators out there, starting if you go back ways from Nano Banana 2 to like ChatGPT Images 2, all the way back to like DALL-E, Stable Diffusion, and all of those methods. So, but they generate natural images. So from what I'm understanding here, computer vision tasks like segmentation and depth estimation are now going to be reframed as an image generation problem. So, and we are going to ask, you're going to like tell these models to generate a depth map instead of like computing a depth map, right? So computing a depth map means you would have these like large language models or even computer vision models which would generate a depth map, or segmentation, you would segment them. So now it's going to generate them directly. So that's something, that's what I'm understanding from this. An invertible false color mapping was implemented to translate scalar metric distances and semantic labels into decodable RGB values. Very interesting. Very interesting to see this part, right? So there are a few more results here, some qualitative results here, and where it says that it achieves like a state-of-the-art performance and other kinds of things. And then what we see is that in conclusion, image generation pre-training effectively functions as a generalist vision learner, providing a unified interface for both visual understanding and creation. Further work will explore scaling task diversity and investigating video generators. Wow, okay. To develop richer temporal aware visual representations. Okay, that's going to be even interesting. So the next AI tool we have is NotebookLM, and I've already uploaded the Vision Banana paper to NotebookLM. This time I also uploaded the project page just so that we get some little bit variety. So we asked her to generate a video and a slide deck. So let's go and see what the video is all about. And this is a cinematic video. So let's get ready to be excited to see what it's come up with.
Teaching modern computers to truly see and understand the physical world is currently a highly fractured, complicated process. Right now, engineers have to build completely separate, highly specialized algorithms for every single visual task. You need one model to identify objects, another to map out surfaces, and a completely different one to guess how far away things are.
So this is so true. I myself, it's very well known in the computer vision community. Like if you want to do some segmentation, there are segmentation models like SAM, segment anything model. If you want to do scale or depth, there is like a depth anything model and so on. And if you want to do like say object detection, there are like methods like Dino or YOLO or RF-Data and so on. So it's what is highlighting is a very true thing that each of these, for each tasks, there are like different models. And just imagine if you want to call all of these models separately, like how many packages need to be installed, how much computation, the memory, all of this would take quite, right? So that's why the problem is being stated as, could we have a generalist vision model which could just take all of this together
to guess how far away things are. 3D spatial tasks are especially difficult. To figure out the physical scale of an object, traditional models rely heavily on complex geometry and need to know the specific internal hardware parameters of the camera that took the photo. Meanwhile, modern AI image generators effortlessly spit out photorealistic artwork with perfect lighting, reflections, and perspective. This gap in performance suggests we're missing a vital piece of the puzzle. We are building narrow, brittle tools instead of teaching systems how to actually comprehend the environment. This led researchers at Google DeepMind to a compelling hypothesis. If an AI can generate a perfect 3D scene, it might already possess a deep internal understanding of depth, physics, and geometry. They designed an experiment to test this by taking a pure, artistic image generator and testing whether it could solve hard scientific vision problems. The base model they selected for this test was DeepMind's own Nano Banana Pro. The immediate hurdle was translation. Because Nano Banana Pro generates art instead of raw data, the researchers had to figure out how to extract measurable scientific outputs from its visual creations. If they could solve this extraction problem, it would suggest that generative models could serve as a foundation for many visual understanding tasks. Instead of rebuilding the model's architecture or bolting on complex new modules, the researchers used a technique called lightweight instruction tuning. This process involves taking a very tiny fraction of specific computer vision data, like depth maps or segmentation labels, and mixing it directly into the model's standard image training set. This minimal intervention doesn't teach the model entirely new skills from scratch. It simply directs the model to output the geometric and spatial structures it has already learned during its initial generative training. The result.
So instruction tuning is one of the one of the prime parts of the large language models. So what you do is you come out with like a series of, if you have at least some new data, you can come out with a series of question answer pairs, and then you give these instructions and saying that this is how you would like the model to behave. Or if you want to fine tune, you could also use these to fine tune and so on. So what I'm sharing from this is that they've adopted this adopted this method for image vision, computer vision tasks as well. So if you have that, okay, how is this segment going to be for this? If that's the question, you have the answer coming out from standard computer vision models. Insert these as lightweight instruction tune to the overall training set, so that it also sees new diverse sets now. And maybe that's what they're trying to see how does it work.
Of this tuning process is a newly formed unified model they named Vision Banana. The success of this tuning suggests that the base model already possessed a deep understanding of visual structure. It just needed to be shown how to express it in a format we can measure. Vision Banana abandons complex data formats. It reframes perception by simply generating an RGB image. Look at this base photograph of a skateboarder midair. By asking for a segmentation visualization, the model draws a color-coded map over the image, isolating the rider, board, and ramp. Ask for metric depth, and it generates a heat map, using a blue to cyan gradient to represent the exact physical distance. This is a 3D diagram showing the numerical color mapping for those depth values. The generated colors map precisely to physical geometries and decodable tubers, allowing researchers to translate the image back into hard scientific data. Asking an AI to draw its answer creates a unified interface that replaces the need for dozens of highly specialized mathematical algorithms. To validate this unified approach, researchers pitted Vision Banana against the world's best domain-specific algorithms. This radar chart compares Vision Banana's performance against several specialist models. In the blue section, it directly beats the highly specialized SAM-3 model on multiple segmentation tasks. Looking at the bottom axis, it also outscores Depth Anything 3 in metric depth estimation. It achieves this accuracy without relying on any intrinsic camera parameters, the internal lens specifications normally required to calculate scale. And despite gaining this massive boost in analytical and scientific capability, the model retains its original artistic generation powers.
So this is so true if you're using classical computer vision algorithms, which are not really deep learning based, or even sometimes deep learning based methods which need some extra information. You need these camera parameters, what they call the intrinsic and extrinsic parameters, which are the focal length and the camera's focal length, and then you have these the camera's optical centers and so on. So these are usually sometimes in the field of view. So these are so important to kind of know exactly how much what the camera, how much that camera is measuring in terms of a photo, and then if you keep changing, if you keep walking with it, how much a change have you done, and so on. And this is required for classical computer vision based methods, and also these numbers could change over time. You have to constantly keep measuring this by calibrating the camera. It's called camera calibration. I myself have done this many times. And you have a checkerboard pattern, and you want to see or some of the pattern, you want to see how much the deviation is from the original values that the camera has to after some wear and tear, how much has it changed or not. So what is amazing in this paper is that it's claiming that you don't need any of these. You can just take the photo as it is, and the underlying AI model is already able to measure in terms of metric depth all of these things. So that's what it's trying to say.
Analytical and scientific capability, the model retains its original artistic generation powers. A single generalist model matching or beating dedicated specialists suggests that generative pre-training is a more versatile alternative to building narrow, task-specific architectures. To truly teach an artificial intelligence to understand the complexities of the physical world, you first have to teach it how to draw it.
Wow. That's a nice way to end. It's like, first teach it how to draw, and only then you could take it to the real world, right? So that was nice. So far we saw like a poster and then a complete cinematic overview for NotebookLM, and I also manually went through the project page to see and understand what I can get. Of course, it's all based on my understanding. The idea is that to see how much a human can understand something, and also how much AI can help in further explaining these concepts. So the last format I want to try for today is that same NotebookLM. I also asked it to generate like a slide deck. So this is I'm hoping that this information is going to be a complementary information to the video that we. So let's see what I mean. Like, this is like, as a human, if I want to consume this from a slide deck, what I can consume from this information. So it says the LLM moment for computer vision. How generative image pre-training is unlocking a universal foundation for state-of-the-art visual understanding, from Google DeepMind. So then, before, the fragmented ecosystem was that you had an image and then you had a custom architecture. For segmentation, you use some model like SAM3, and for depth, you use something like depth anything v3, and then for something, I don't know what Lotus 2 does. I was mentioning this in the previous video, right? When we saw the video, for each of these tasks, you have different models, and imagine how much you load all of these models, how much computation, space, and all of these take. What if a single model can do all of this? That'll be really moving the needle. And now the universal funnel. Just give a prompt and just have some like a model like Nano Banana Pro, which is a generation model. Ask it to generate an RGB image, and can that lead to unified visual understanding? Historically, discriminative models required heavy architectural specialization. So these are the discriminative models that you're talking about. So usually the models are divided into either discriminative models or generative models. So Vision Banana proves that a single generative model can resolve training target ambiguities by design. So this is the universal interface. So I really like this picture because it's different from what we saw in the cinematic video. Here it's more like, so the first step is the prompt. So you have a cat and you color it red, you have a lock, you color it pink, you have an exit sign, you color it like light purple. So you're giving all of these kinds of instructions beforehand. And then you do, the step 2 is Nano Banana Pro. These are fed into Nano Banana Pro in a lightweight instruction tuning, seamlessly processes the text constraint. So these are the text constraints you have, right? So Nano Banana Pro takes these as input and tries to process that. And what we get here is an RGB output. The model generates a strict multicolored image based on these kind of initial in the constraints that we provided, right? That's what it tries to get. And then you decode this. They're trying to see is it really coming out well or not. So we wanted the cat to be red. Is the cat really red? We wanted the lock to be pink. Is the lock really pink? The exit sign is light purple. Is the exit sign light purple? So colors perfectly map back to usable computer vision data and values. Right? So as a human, if we can tell this, in computer vision we are used to some standard color maps, heat maps for different things, like there is this jet color map which is usually used to denote some things, which is goes from red to yellow and to blue, and then there's the other color map we saw which is for surface normal and so on. By parameterizing the output space of abstract vision tasks as bounded RGB images, perception is seamlessly reframed as image generation. Ingenious idea, ingenious. Vision Banana achieves state-of-the-art across three distinct domains without specialized architectures. So again, very important part here is without specialized architectures, which means without a SAM3, without a depth anything V3, or without a Lotus V2, it's achieving state-of-the-art. It's much better than any of these, right? So 2D understanding surpasses SAM3 on cityscapes. Cityscapes is one of the data which is for semantic segmentation, urban scale, which is usually used. And so you can see that SAM3 is somewhere here, and this is much better than that. And then 3D understandings beats depth anything 3 model on metric depth, so that's one of the state-of-the-art. And generation rivals Nano Banana Pro on Gen AI bench. That is amazing. It's also really good in generation, right? So they've shown that this is what Nano Banana Pro is coming to, and it's almost as good as that. Maybe it's slightly better even. Right, so that's pretty cool. The instruction-tuned generalist rivals or surpasses highly tuned task-specific specialists on their own turf. Bounded semantic control, so 2D, so 4.7 points higher mean IOU intersection over union, which is usually the metric used to measure segmentation, semantic segmentation. Then SAM3 on cityscapes. So here's an insight. Instead of training on vast amounts of human annotated mask data like these, we tap into the rich representations inherently learned by the base image generator. That's really cool. Nuanced reasoning beyond edges. So you also I think we saw this in the example from the project page. So you have recognizes the cat, cleaning cat, and differentiates the pose, differentiates based on pose stretching cat. So you can see here that you have a zero-shot state-of-the-art on reasoning segmentation. So it has basically here you're supposed to say that it's just a cleaning cat, and here it's supposed to say that it's a stretching cat. The multimodal intelligence inherited from generator pre-training allows Vision Banana to reason about what to segment, not just where the edges. So here it's combining reasoning with segmentation. That's totally super amazing. Then the next one is the unbounded challenge, inferring 3D structure. So the question is that can you actually get the 3D structure in terms of depth, surface normals? 2D tasks rely on flat bounded color spaces, but 3D metric depth is unbounded. Basically, you could go from 0 all the way to infinity. How does a generative model constrained on RGB from 0 to 1 understand infinite physical space without relying on multi-view camera intrinsics? So then you have the RGB bijection, curving distance into color. So they have this kind of a representation here. So you have this curve. Metric depth is warped using a power transform, lambda is equals -3, to prioritize near field accuracy. So I think from what it's trying to say is that it tries to how log and power loss and all happen, and something is close by in a range, they try to constrain it beyond that, and if it goes really far, they may even make it bigger, go beyond that range. So that's what I think. Again, not sure, this by curved distances, basically instead of just being everything linear, you have something like a log or exponential or a power, something like that. These curved distances are interpolated along the edges of the RGB cube from black to white, and then inward. At inference, the generated RGB images is decoded seamlessly back into precise physical distance values. So, and this is beautiful. I love this comparison. Zero-shot monocular metric depth. So earlier during the cinematic overview, I was mentioning that almost all the previous methods require these camera intrinsics. You need to know the focal length, the optical centers, and you also need to know whether any deviations has happened. So the calibrated way. And Vision Banana here, you don't require this, and not only you don't require it, it's much better in terms of accuracy, even without requiring the camera intrinsics. It's that's too good to be true. So Vision Banana achieves state-of-the-art across zero-shot benchmarks, beating depth anything 3, unique K3D, relying entirely on internal visual priors of object scales rather than extrinsic camera data. Zero-shot validation in the wild. So this is extremely important. Almost in all papers, I feel that it's really good when results are shown on like some good images from the training set and validation set. But rigorous evaluations are needed if in the wild, right? You have to take lots of images in the wild from different categories and see how it performs. So here's an input photo, here is a generated depth map for this, and here is a satellite ground truth. That is actually like, this is really hard, because this is at least you've seen that you can know there's a tree and the house. Many image models would have seen this. Satellite is like almost everything looks really small and flat, and there's not much variation. So that's actually nice. Absolute relative error of just 0.065 on completely unseen, uncalibrated sensor. Amazing. Surface normal estimation, geometry proxy. I think we saw that there is in the video that showed the color map, right? It started something like red, bottom red and then it started going like this and something. So it says facing left is pinkish red, facing up is like light green, and facing the camera is light blue. If you remember, I was mentioning that like surface normal are usually vectors, and then they are like, if you can take a surface and how those vectors, like what direction they turn in and things like that. So here is the color map, which has that. Data proof averages the lowest mean and median angular errors on a few data sets, outperforming Lotus 2, which is probably the previous state-of-the-art method. The generative approach produces maps with significantly finer granular details and higher visual quality than discriminative methods. No catastrophic forgetting. Vision Banana and Nano Banana Pro, they have a comparison. 53.5 Vision Banana is 53.5% human evaluation win rate versus base model on text to image generative AI bench. 47.8 win rate on image edit. So catastrophic forgetting is something which, like, if you keep like asking it more and more things, it tries to forget what the initial thing was, and it starts deviating. So this is, I didn't see this in some of our previous either in the video or in this, so it's nice to see if this is actually true. Lightweight instruction tuning aligns emergent representation without regrading the foundation model's original generative artistic bias. One model to rule them all. Like you have SAM3, this is segmentation, semantic segmentation. So this is like, and then you have SAM3 agent reference, recent segmentation, and then you have depth anything with. So you can see how this was Vision Banana. This is better in all of this in each of these tasks, right? So this is semantic segmentation. This is 0.65, this is 0.69, and SAM3 reasoning segmentation. This is 0.77 and this is 0.79. Depth anything V3 on metric depth. This is 0.91 and 0.92, and Lotus error. This is the error. All the other three are like IOU or accuracy. So this is Lotus 2. It's like 19.64 and 18.9. The difference may be small, the average difference, but again, look at the fact that you don't need each of these three models. If I was coding this up in Python, I would have had to like install each of these models, which itself is a real pain, and then make sure all the libraries, all the packages, everything works, and then like each of these models will still occupy a lot of space, and then it'll take time for the inference for all of these to happen. And if now one model can do all of that, just imagine the possibilities that are going to come up. I wouldn't be surprised. I wouldn't be surprised. I should maybe come back at a later time. I don't know which conference this paper is being submitted to. I wouldn't be surprised if this wins the best paper award. So Vision Banana, best paper award. Let's revisit. We are right now in 28th April 2026. Let's revisit. I'm going to say when Vision Banana gets the best paper award. So let's see. By treating every task as an image generation problem, a single set of shared weights surpass a highly fragmented ecosystem of domain specialists. The road to AGI. The road to AGI Vision. Wow. The road to AGI Vision, artificial general intelligence from Vision. I always think Vision could be faster to achieve than, say, text and other things. I'm biased because I'm from this field than text, but historically we've seen that this happened a lot of times. Is that there used to be a lot of progress in text and natural language processing, and then they would make it out of Vision, and the results used to be like really different. The model doesn't know it's calculating metric depth. It doesn't know it's performing instant segmentation. It is simply following the text instructions to generate colored pixels. Image generation isn't just a tool for making pretty pictures. Generative pretraining is the foundational word engine required for true machine understanding. We have found the universal interface. That's it. I always love the fact that it comes up with some great finishing touches. So this has been one of the most exciting papers and projects that I have come across. And let me tell you again, I wouldn't be surprised if this wins Best Paper Award. I think this is going to be one of those groundbreaking papers that come from time to time. And it's amazing how we saw, like, from, as a human, I was trying to see from the project page what the paper is talking about. And then we passed the paper through some AI tools like SaralAI and NotebookLM, which also kind of tried to decode what the paper is about in a very short form. Of course, if somebody is going to do a deep dive, I would want to go deep and read the paper and try to understand the concepts more. But this is like what we're trying to do here is like a quick grasp of a paper and what it's about using just some AI tools. And it's amazing to see how Vision Banana tries to build a single framework both for a lot of computer vision tasks such as like segmentation, like depth estimation, object detection. Object detection was not here, but I think that also would eventually come with it. And then also achieves really good results in terms of image generation, right? These two have traditionally in the computer vision field, there have been two different methods, right? They have been like one does discriminative and the other one is generation. You have these object detection models, lots of these models, and then you have like image generation models, a few of them. And like I said, if there's one single model which does all, imagine from a real practical scenario, you don't have to install so many models. You'll save on memory, you will save on time, and so many other things. So if this one model is better than all of the other models in terms of like accuracy or error, I think this is really going to change the game and move the needle. So until next time, I will take a look at another exciting paper in Decoding Papers with AI, Relax AI channel.